Welcome everybody to the DSI's Data for Good speaker series. I'm delighted today to introduce our speaker, Dr. David Hogg. David is an astrophysicist at NYU's Center for Cosmology and Particle Physics. He also leads the Astronomical Data Group at the Flatiron Center's Center for Computational Astrophysics. His work, as you'll hear momentarily, is extraordinarily broad. He touches on cosmological measurement, engineering and instrument calibration, statistical inference, and open source data initiatives. His academic training is in physics, first at MIT and later Caltech. And David, thank you for being here. We're delighted to host you and looking forward to your talk.
Thanks very much, Martha. It's fun being here. I was one of the founding members of the NYU Center for Data Science, and it's really fun to see the Columbia Data Science Institute here, and just the enormous growth of data science in the city has been amazing, both academically, like with our institutes, but also in the industrial sector. And I'll mention a few things about industry at some point in the talk, although I'm not so nice necessarily. Good, so I'm going to talk about an overly mathematical topic. Ordinarily, when I give a talk like this, I would tell you about astronomy and cosmology, but I'm going to talk more about like the structure of machine learning, and it's a little bit mathematical, and I'm not a mathematician, so I'm going to be a little vague when it comes to the proofs and so on, but I'm going to give you some sense of where we're working mathematically in data science. Good. So one thing I wanted to say is that this is the Data for Good seminar, but actually most of astronomy is done really to satisfy curiosity. It's not really, in fact, sometimes we joke in astronomy that we're doing like the least ethically valuable of all the sciences, because really there's very weak connections to the real world. I should say though that two of my collaborators, Soledad Villar and Ben Bloom-Smith, there's an and swapped in there, it should be Soledad Villar and Ben Bloom-Smith, do work in data and fairness. And in fact, they started the Data and Democracy seminar at NYU, which is a great seminar series. And if you're interested, send me email and I will link you up with them. There are some data for good or ethical things to think about in astrophysics, and I actually work in all of these areas at some level. Like for instance, we run big public facilities. We work on big shared facilities like the Hubble Space Telescope and observatories around the world. And so this has to be like fair and transparent. We work with amateur astronomers and citizen scientists on a bunch of projects, and there's a lot of considerations about using data and information from human subjects there. And we produce enormous public data sets. In fact, astronomy is like a model for open science. Our data and our code tend to be public. For that reason, when we do things, you actually can impact a lot of scientists. So if you do something wrong, you can impact a lot of scientists. And I'm not really going to talk about any of these things, except that I'm going to try and connect to explainability and interpretability, which is related, of course, to transparency and ethical considerations. So what I'm going to say is I'm going to talk about classical physics, and I'm actually the first third of my talk is going to be just reminding you of things from introductory physics, or maybe telling it to you for the first time, depending on your background. So I'm going to just remind you about some like basic ideas in physics, which maybe you haven't thought about for a while. And then I'm going to show that if we write, or say more than show, but we have shown to some extent that if we write a data analysis model in the same language as physics, that's a very effective thing to do. So you'll see that coming back. I just want to say right here that this work is all in collaboration with Soledad Villar at Johns Hopkins. She is a applied mathematician who works on the mathematical basis of machine learning and data analysis problems. And this collaboration is truly interdisciplinary. And then Ben Bloom-Smith is a pure mathematician at NYU who's helped us a lot with the like truly pure parts of this. You'll see there's some pure math appears in a minute. And just as an introduction to myself, I work on measurement problems in astronomy. I like measurement problems that are difficult, and they can be difficult because the data are large, but they can also be difficult because the signals are kind of hidden in the data. And that happens a lot in astronomy. Astronomy is an observational science, so we don't get to choose our data or how it's generated. we get what we get. And I also produce big open data sets and big open code bases, and I maintain those. And we kind of have an open science role in astronomy in my group. And I collaborate and co-advise students with people from statistics and math. And this is going to be in that area. But I'm not, I have to say, I should admit, though there's machine learning in my title, we're not really a machine learning shop. In fact, in the community, I'm known as a bit of a curmudgeon about machine learning. And I tend to use simpler models like linear regressions and polynomial regressions. And I don't use, 42-layer ReLU networks in my work very much. But part of the reason I've been kind of like avoiding the deep learning world is because I felt like it's a little uncontrolled. And this talk is about like controlling that complexity. Okay, so now is the part of the class where we talk about intro physics. And I have to say my two loves are data analysis and introductory physics. I've taught introductory physics since 1993, from which you can compute my age. One of the things I emphasize a lot when I teach intro physics is what are scalars, vectors, and tensors. So in high school, people tend to get an idea that a scalar is just a number, and a vector is something with a magnitude and a direction, and a tensor is, well, they don't even hear about tensors. But these are trivial. Those are not correct. That's not what scalars, vectors, and tensors are. The important thing about scalars, vectors, and tensors is that they are coordinate-free entities, at least as those words are used in physics. Those are coordinate-free entities. So a scalar is something that is the same in all coordinate systems. It's something with a magnitude and units that is the same in all coordinate systems. So it doesn't matter if I rotate my coordinates or translate my coordinates, that scalar will still have the same value. So they're coordinate-free objects. And then it's a little complicated to understand how a vector could be a coordinate-free object. But it has to do with the consistency of directions or dot products between the vectors and so on. There's a sense in which a vector can have a direction that is coordinate free. One example I use in class sometimes is I have everyone imagine a coordinate system, and then I have everyone point in the x direction, and they all point in different directions. And then I say, now point in the direction of the acceleration due to gravity, and they all point downwards. And that shows you that the direction of gravity is well defined, even though your coordinate system could be different. And importantly, physical law has to be independent of coordinate system, because there is, like, God didn't give us a coordinate system. So since a coordinate system is always a choice, physical law can't depend on it. And then tensors are like higher order objects. I'm not going to talk much about tensors in this. I'll name check them a few times, but we won't really talk about them. But if people want to ask questions about tensors, I'm ready to go. I love tensors. And of course, tensors are the basis of a lot of physics. Okay, so next point of introductory physics is dimensions and units. Every physical quantity, every scalar, every vector, every tensor, and every operator like d by dt or whatever, or grad sub x or whatever, has dimensions and it has units. So for instance, an energy has dimensions of mass times length squared over time squared, or it has units of joules, which are kilogram meter squared per second squared in the SI system. So there's every quantity has well-defined units and dimensions. And there's an algebra, or it's not exactly an algebra. Actually, my mathematician friends tell me it's not an algebra. Okay, fine. There's algebraic rules that connect units. So for instance, if you multiply two quantities, you multiply their units. If you divide them, you divide their units. And if you want to add or subtract two quantities, they have to have the same units. Though that's a very strict constraint on physical law. Actually, it turns out that constraint is exceedingly strict and really reduces the capacity of physical laws. So a little more intro physics. So there's some standard symmetries that basically all of classical physics obeys. All of classical physics basically obeys symmetries of the orthogonal group. The orthogonal group is rotations plus flips. And then there's a little debate among physicists to whether it's the orthogonal group or the rotation group, and I will die on the hill that is the orthogonal group, not the rotation group, but the story is slightly different if it's just the orthogonal or the rotation group. Then there's translations. You can so what do I mean that physics obeys these symmetries? It means you can rotate the coordinate system and it doesn't change your problem. That's the rotational symmetry. You can flip the coordinate system through a mirror. That's a parity flip. Doesn't change anything about your predictions or your answers. You can translate your coordinate systems, nothing changes. And then there's a more obscure one. So like Lorentz is the symmetry of special relativity. That's the thing that ensures that events that are in causal order remain in causal order, which relates to causation and the causal structure of the universe. So there's Lorentz group. And the permutation group, meaning the laws of physics don't care about which order you consider the particles or how you list the particles or labeling of the particles. In fact, that group is actually very strong and it has a very fundamental role in quantum mechanics, actually. Anyway, these are kind of the symmetries of classical physics. And then of course, there's additionally this units and dimensions symmetry that I mentioned in the last slide. Okay, now getting a little technical. So now we're going to start to get a little technical. So that's all very simple. Here's something that you don't actually learn in intro physics necessarily. And that is that all the laws of classical physics, possibly quantum physics too, but anyway, let's stay with classical. All the laws of classical physics can be written in a notation which is called summation notation. Sometimes it's called Einstein summation notation, but that's a bad name because it wasn't invented by Einstein, but it was brought into physics by Einstein. It comes from geometry, and it's a notation that if when physicists learn this notation, they learn it as a convention, but actually it's a very strict constraint on physical law. And let me just show you what the constraint I mean, there's too much to say here, but let me just give you a little bit of a sense. If you want to do the dot product of two vectors, that is vectors u and vectors v, they have components I, like that's the x, y, and z component of the vectors. Then you can think of the dot product of the two vectors, the scalar product of the vectors, as being the sum over the components of the two components multiplied by each other. So the x components multiplied together, y's, and then z's. And that's the same as doing like u transpose v if you think of the vectors as being column vectors. And in Einstein summation notation, you just write it as ui, ui. And that repeated index is implicitly summed. In Einstein summation notation, if you repeat an index, implicitly it's summed. So this notation by definition is the sum over the indices of ui, vi. And then there's the next rule of Einstein summation notation is indices can only appear either once or twice. You cannot write ui, vi, wi. You can never do a sum over three indices in physical law. And that's a very strange fact, but it has to do with the geometry, the geometric properties of physical law, that if you multiply three things together, then all of a sudden the rotational symmetries of the problem will not work. And then a general expression will have some indices repeated, some indices not repeated. The sums will be over the repeated indices, and the unrepeated indices will tell you the order of the resulting tensor. And this is a way of writing physically correct expressions in physics. And that's a little bit inside baseball for everyone. I'm telling it to you because it's like a hint, it's like a motivation. It's like, how did we get to what I'm gonna start talking about data science and like, how did we get there? And this is one of the key clues we had, that there was a structure we could take advantage of. By the way, this is not just a game. Einstein in around 1908, maybe learned from Ricci, or really from Levi Civita, I think, learned that there was this summation notation that would ensure that his quantities had good physical symmetries. And then he literally searched by hand, brute force, over all rank 4 or order 4 tensors that he could write down with certain differential operators. And he found the general theory of relativity by searching exhaustively in theory space over things that met the symmetries plus the units requirements. And nowadays we would think of what Einstein did as like a symbolic regression, because he kind of wrote down all the possible polynomial terms that could be his theory, and then fit to the data, which actually, by the way, the data was Newtonian gravity. He was trying to reproduce Newtonian gravity at weak fields. And there was one answer that worked, and that turned out to be general relativity. And that theory has survived to the present day. That was correct. So this is one of the reasons that physicists love this notation, is it actually created general relativity. Okay, good. So now that was the intro physics. Symmetries matter, units matter, Einstein summation notation, important. Okay, good. So how do we use machine learning in astrophysics? I'm a card-carrying astronomer, and on different contexts, I call myself an astronomer or an astrophysicist. Where do we use machine learning in astrophysics? There's many places. This is not an exhaustive list. Here's just 4 examples of the kinds of problems I personally work on in my own research. The first 2 are about simulations. If you have simulations of the universe, the question is, can we make faster or higher performance versions of those simulations using machine learning? So can we train a machine learning model to replace a simulation or to accelerate in a simulation? And I call those emulators and translators. There's translators that translate from rough, like low resolution simulations to high resolution simulations. And there's emulators that directly replace the simulation. We work on that. And then we do things where there's nuisance parameters. So we're observing, I don't know, the large scale structure of the universe, and in the way, there's all sorts of stars and gas that is filling the field of view. We don't care about those things. From our point of view, they're nuisances because we're trying to study the galaxies in the background. And so we can model those foregrounds using flexible models from machine learning. And then we do classification tasks where you have a lot of high throughput things. We're actually, astronomy is now a very high throughput field. I'm working on a project called Sloan Digital Sky Survey 5, and that is producing, I don't know, 100, 200 high quality spectra of objects a minute. And we have to apportion those objects to pipeline units, and we have to do classifications on the fly. So those are the kinds of places where machine learning is being used in astrophysics, but there's lots more. That's not supposed to be an exhaustive list. Those are the things like I think about. And one really important point that I want to emphasize is that the natural sciences are not like industrial data science. So we were talking before this started with Alex about the industrial partners of the data science institutes. And the questions that our industrial partners are asking are generally very different from the kinds of questions we're asking in natural science. In industry, you're often asking, can I predict future data that are very similar to the data that I have taken previously? Whereas in natural science, that is very rarely our goal. Usually our goal is to understand the latent structure of a model, understand what's really going on, make an explanation for the world. And so the standard methods of doing data science are kind of almost at odds with natural science, because the standard kind of data science methods are very black boxy and about predicting data with data, whereas we're very interested in explanations and predicting latent things with data. Like, for instance, we like to know what were the initial conditions of the universe, what are the properties of the dark matter. Things that we can't observe directly is what we're trying to understand. So actually, black boxes are kind of the worst. Good. So one of the reasons that I emphasized emulators and translators in our work and in this project is that first of all, these are areas where the way we use data science looks a lot like industrial uses of data science. It's a place where you have training data, where you have like low resolution simulations and high resolution labels, and you want to infer the high resolution labels using the low resolution simulations. It looks very like you have customers who've done certain things and you are trying to predict what they're going to purchase next or whatever. And the other reason we love these kind of areas is it's a place where the symmetries are exact. Like when you're doing a simulation of the universe, you're literally simulating a homogeneous, isotropic, translationally invariant object. And so we actually believe in those contexts that our symmetries are exact. The symmetries of classical physics apply exactly. So when we're thinking about like, how does first year physics impact data science in the emulators, really it's very directly. So just to make sure everyone's on the same page, I've been using the word regression. I want to use it very carefully now. So I'm going to talk about regression. And in a regression, you have a set of training set objects. You have examples of things, which could be simulations. And those things have features and labels. And often in regression settings, people think of the features as being a big set of things and the labels being one thing, but that's not going to be true here. Here, the features will be a big set of things, like the positions of all the particles in some simulation, and the labels will also be a big set of things, like positions of particles in a simulation. So you're trying to take maybe one simulation and trying to predict another, or you're taking initial conditions and trying to predict final outcomes, or the other way around. You see the final outcome and you're trying to predict what the initial conditions were. So the features is a big thing, a big set of observations, and the labels is also a big thing, a big set of like latent properties. And the idea is to try and learn a function, which is a high dimensional function that takes the features in and returns the labels, or returns an approximation to the labels or a good estimate of the labels. And then you apply that to new data. So that's what I mean by regression, which I think is generic. So now, what do we mean for us to impose the symmetries of classical physics? And one of the funny things, you can see the last line of this slide, is that physicists call something symmetry, and the mathematicians call that same thing equivariance. And I'm a physicist, so I will often use the word symmetry, but if you're more mathematically inclined, you can translate to equivariance when I say it. And the simplest example of an equivariance of this kind is that if you have a regression where you have a bunch of vectors coming in, like maybe they're the velocities of a set of particles, and you're predicting a label, which is also a vector, say it's like the acceleration of something. If you rotate your coordinate system, so all of those vectors rotate in the same way, then your output of your also has to rotate in the same way. So that's called equivariance. If you rotate the coordinate system and it changes the values of the coordinates or whatever of your vectors, then it also has to change the coordinates of the output vectors in exactly the same way. And I think I have a mathematical statement of it next. Yeah, so in the paper that Soledad led, this is the statement of equivariance, that if you have a group element G, so if you have a group, which could be like the rotation group or the translation group, or the Lorentz group or whatever. So you have some group, let's think of it as rotations right now, because they're the simplest ones to think about. Then if you apply an element G, little g, from that group, and if you apply it to the inputs of the function is invariant if that function is unchanged by that group action, and is equivariant if when you apply that group element to the inputs, you get that group element applied to the outputs. And that's the case of this rotation. The reason that physicists and mathematicians use different language here is a little bit subtle, and this is like really inside baseball now, so you can just check your email for a minute, but it's because in math, people tend to think about taking the vectors that are input to the problem and rotating the vectors. Whereas in physics, we tend to think of the coordinate system and rotating the coordinate system. So in math, the kind of picture people have is if you rotate the input vectors, you have to rotate the output vectors. But in physics, we tend to think of like, if you rotate the coordinate system, nothing changes. And that's why physicists call this a symmetry and mathematicians call it an equivariance. And that's a little bit of a barrier in discussing things sometimes between physics and machine learning. Okay, good. So why does enforcing equivariances help you? If you're doing machine learning and you're in a natural science context where you know that there's equivariances of important symmetries, why does enforcing them help you? It's very simple. So imagine you have a machine learning problem where you have a lot of vector inputs and you're trying to get a vector output or a set of vector outputs. And imagine you have no idea about machine learning or whatever. So you just build a polynomial. You're just like, okay, I'm gonna use a polynomial to predict my outputs because I don't know anything about ReLU networks or whatever. I don't care. I'm just gonna do a polynomial. So then what do? You write down all the polynomial terms of the inputs that you can possibly write down. And that's a huge number of terms. If you have a few hundred vectors in three-dimensional space and you write down like the degree 4 polynomial you can make out of those, it's extremely large, like much larger than will fit into RAM. But now you can ask, what polynomial terms are there at degree 4 that satisfy the constraints of the Einstein summation notation that we talked about a few slides ago? And the answer is enormously fewer. So the idea is that when you apply the symmetries, you end up enormously reducing the number of things that can happen. So for instance, when you have translation symmetry, the position vectors can't just come in willy-nilly. It always has to be differences of position because nothing can depend on the absolute positions. If you have rotations, only dot products of vectors can enter. You can't be just the vector components. It has to be dot products of the vectors. If permutation symmetry is on, then it's not like all the vectors matter, but only certain sums of the vectors that are permutationally invariant matter. So it enormously reduces the number of terms in your polynomial and enormously reduces the model freedom. And then it's even more extreme if you include the unit symmetry. So this is just immensely reduces the size of your model. And one thing that's very, very important is that if you can reduce your model capacity without reducing your complexity, so you're still a degree 4 polynomial, but you've gotten rid of all but 1 in 10 to the 4 of your terms. So like your polynomial just got 10,000 times smaller, then your model capacity has gone down by a factor of 10,000, even though your model is just as expressive because it's still a 4th order polynomial. It's just a 4th order polynomial that removes all the terms that can't possibly be there for deep physical reasons. And that protects you against overfitting. It protects you against adversarial attacks. It's very, very good to be able to remove terms. Okay, good. So now I'm gonna, that was all, believe it or not, that was all introduction. So now I'm gonna relatively quickly go over the results of some of the work we've done, which is overly technical because the main point I wanted to make was actually that, exactly what I just made, that if you enforce these symmetries, you have a much reduced capacity at same complexity and you're better off. Good. So this paper, the work that I'm talking about is in a few papers and there's more coming, but the key paper is this archive number. I only give archive numbers in the slides, so you'll have to look on archive for the papers, but this is going into NeurIPS, I guess, this month. It's called Scalars Are Universal, and it's about how to construct equivariant data analysis methods when you have scalar, vector, and tensor inputs. Just looking a little bit at the chat.
Yes, there are a couple questions in chat.
Yeah, about data, best practices in data.
I don't know if you want to take them now. If
yeah,
not,
so let me just say a word or two. Yeah, before I get, because it's going to get very technical now. So let me just say, yeah, industry is happy with black box algorithms, what does it mean? So I think this is changing a lot now. I think the industry has been, so the question is about black box, like is industry really just black box? And if so, what's data science connection to industry? And I definitely think that the industrial world is moving to much more interpretable and explainable systems. I think it's a very exciting thing. And if you look at the big conferences, there's so much work going on, explainability, interpretability. So I think that landscape is changing a lot. But I just think that industrial data science is just a different beast from scientific data science. And we should see each other as contributing ideas and thoughts to each other, but really they're parallel and different developments. But that's a bigger question. Do you claim that all manifolds in computer vision satisfy the summation notation? I think the answer to that is yes, that in computer vision problems, if you are predicting observables, coordinate-free observables, it must be possible to rewrite any method that's being used in the summation notation. It's a very strict rule. It has to do with the observations that we make being coordinate free. So there's a very beautiful idea that all observations that are ever made by humans are coordinate free scalars. They have to be, because the world doesn't provide a coordinate system. And if you measure what you think is a vector or something not coordinate free, it is coordinate free if you think about it as being relative to the orientation and location of your measuring device. So there really is a very deep idea in theoretical physics that all observations are coordinate-free objects. And so you can always write any prediction of an observation or any fundamental theory in this form, I think. Exceptions would be remarkable. So it's interesting to think about it. Okay, good. I'm going to talk about this paper. So the idea is, the setup of the paper is that you have scalar, vector, and tensor inputs, and you're going to work in a physics problem, and you're going to produce scalar, vector, or tensor outputs. And the fundamental observation of the paper is actually very, very trivial, and it's old. It's an old idea from the theory of invariant functions, which is that you take all of your inputs, which are scalars, vectors, and tensors, and from them you build all the scalars that you can. So the scalars are already scalars. The vector inputs, you can dot them into each other. And then the tensors, you can do certain kinds of contractions. So once you've dotted the vectors into each other and contracted the tensors and vectors into all the scalars that you can, then any function you can make that is invariant with respect to your coordinate system will be a function only of those scalars, or can be rewritten as a function only of those scalars. So it really is a very strict rule that if you're going to build a rotationally and translationally and permutationally and whatever invariant function, you can do so by creating the rotationally, translationally, and permutation invariant scalars, and then just making your function a function of those. And that comes from the theory of invariant functions. And there's some small adjustments to this if you have rotation symmetry, but not parity. It's a little complicated. One of the things that's nice is the symmetries of classical physics always include parity, and so we're always OD. But if you were in SOD truly, you would have to make a small adjustment. And then if you think about Lorentz symmetry or boosts in special relativity, you have to use a non-trivial metric when you take your dot products. So there's a little bit of details. There's some footnotes on that, but this is very important. And this is the basis of everything, because now the idea is, now if we want to make equivariant vector functions or equivariant tensor functions or any higher order things, then the way we do it is just the same. You build all the scalars that you can. Now imagine we're going to do an equivariant vector function. So now we construct all the scalars that you can, and then you construct all the vectors that you can. And then your equivariant vector function has to be writable as a sum of scalar functions of the scalars times those vectors. So really, all the non-trivial functions are functions of the scalars alone. You can't do a non-trivial function of the vectors, you can only do a non-trivial function of the scalars. Another way to say it, which was surprising to some of my collaborators when we first started working on this, is that the equivariant vector function has to live in the subspace spanned by the input vectors. You can't get out of that subspace because you only have scalar functions times those input vectors. So that's like a restriction on physical law, which, by the way, is obeyed by all of classical physical law. We actually, in the paper, we comment on some places in physical law where people think it might not hold, and we show that it does hold. And here's the statement. Just to show you the math from the paper, here's the statement of that in the paper. H of V1, V2, Vn is a vector it's an equivariant vector function of vector inputs. And and that can be written as a set of f sub t, which are scalar functions, times those vectors v sub t. So you can always write this vector function as a sum of scalar functions times vector functions. And now you might ask yourself, what does that have to do with the summation notation? It turns out this idea is encoded exactly in the summation notation. I'm not going to go back to that, but it is, and that's where we came. That's how we arrived at this. This proposition is proven in the paper that's cited there, and the proof follows relatively straightforwardly from the theory of invariant functions. So it was definitely outside of my expertise. That proof, I did not understand it at first, that this was easy to prove, but it was straightforward to prove this. And of course, being a NeurIPS paper, it's a requirement that you turn on some toy data and prove and demonstrate something. So this is a companion paper by Weiqi Yao, who's a graduate student at NYU. And she studied this what we call the springy double pendulum, which is a classically chaotic object in physics, so mechanically chaotic. It's in the if you're mathematically inclined, the KAM theorem. This is the simulations we're doing are in the KAM regions that are chaotic. And then there's some example trajectories shown, and the solid lines are the true trajectories, and then the dashed and dotted lines are predictions from a model that's based on the scalars. So this is like predicting chaotic dynamics using a data-driven model. Look at this, a beautiful, beautiful question. In 3 dimensions, the cross product of 2 vectors is not in the subspace spanned by the 2 vectors, but is equivariant, right? Excellent question. Is the cross product, so going back here, is the cross product. So that's such a good question, because that's really gets at the detailed mathematical structure. So if your symmetry is OD, there is no cross product. The cross product isn't allowed because the cross product violates parity. And actually, there's so much interesting stuff about pseudo vectors. So from our point of view, cross products produce pseudo vectors, not vectors. And they're pseudo vectors because under parity, they change direction. And so if you have OD acting, then there is no cross product and no adjustment has to be made. But if you notice this little note, there's a small adjustment for SOD. If you only have SOD and no parity, then there is also a cross product that comes in. Anyway, it's a beautiful little detail. And actually, we spent weeks and weeks discussing the mathematics of that. It turned out to be complicated, and then it ends up having a simple answer. Okay, good. Where are we? Good. So this is just a toy problem, working on a toy problem using the thing. What we do is we put in these, you see that on the left, there's vector and scalar inputs. The scalar inputs are like the strengths of these springs and the lengths of the springs and the masses. And then the vectors are like the vector due to gravity, which is the green G, and then the positions and velocities of the 2 masses. So this is a system that has like 5 vector inputs, G, 2 positions, 2 velocities, and then a bunch of scalar inputs. And then we can construct all the scalars and build everything. So it works. And then one of the things that Weiqi showed is that it works way better than the alternate methods that are available. And so the purple line is us. This is a mean squared error. The other colored lines are other kind of physics-oriented machine learning methods that we're competing with. And this works very well. But I wanted to say, I'm running out of time, but I wanted to say that the thing that is kind of most amusing about it is we didn't have to rebuild those methods from scratch. It's not like we threw away those methods and built a totally new method and got it to work better. No, all we're saying is you just replace what are the inputs to the bottom layer of your neural network, and then make a small change to the structure of the top layer of your neural network, and that's it. So in fact, the way Weiqi made these results was literally to take a published method by Finzi et al., it's mentioned down here, and just modified their exact machine learning method and just betterized it. So this is like a simple way to take a functionally, like a capable machine learning method and reduce its capacity at fixed complexity, and you just do better. You get to the same performance with much less training data, or better performance with the same training data. Good. I just threw the groups back up here because I knew that I would spend too much time talking about rotations and not enough about the other groups. All of these groups are handled in this framework. So in this framework, what you're doing is finding invariant scalars that are invariant to all the groups. And once you've enumerated all the invariant scalars, you're done. You don't have to go any further. And I've focused sort of on rotation translation, but permutation and special relativity boosts are all there. Okay, now the objection you should bring up is real data sets break symmetries. That is absolutely true. Real data sets are not exactly symmetric. Physical law is symmetric, but we live at a certain location in the universe. So even if the universe is homogeneous, our view of the universe is inhomogeneous because of our specific location in the universe and the anisotropy of our observation model. So how does this work? And the answer to that is going to be, and I don't have this yet, but the answer is going to be to complexify the causal structure. So the idea is your observations are an observation model acting on a symmetric physics model. So there's a symmetric physics model in a latent space, and then your observations are related to the symmetric physics model through some observation model, which does itself break symmetries. So in the long run, this kind of approach is just a component of a much bigger, more sophisticated model. And this is what we're working on this right now in the context of cosmology, how to make a cosmological model that has exact symmetries in a latent space, but then is observed through an observation model that is asymmetric. And we've done a little bit of work in this area. I quote one paper there, but there's various things we've done in this area of like causal structure, but it's out of scope for today. I should say, I'm not going to really talk about dimensions and units, but I just want to flash up here that dimensions and units can be handled exactly the same way. You actually do, exactly the same thing where you produce invariants, which are dimensionless quantities now, and you produce dimensioned quantities, and you multiply dimensionless functions of dimensionless quantities times the dimensioned quantities. It works beautifully. And it reduces the model capacity even more than the classical physics symmetries, we think. So this is an extremely strong constraint on physical models, and it's going to improve our results even further in those toy problems. Just to summarize, I'm in the summary part. So the idea here is to construct invariants and then build equivariant functions out of sums over invariant functions of the invariants. And this is a powerful framework for physics. It is literally the basis of classical physics since 1908 or so. And it turns out that it's a useful idea in machine learning. We think, I mentioned earlier on that You can think of Einstein's discovery in 1915 as being a symbolic regression success because he wrote down the terms that could exist that were satisfied the symmetries and the units, and he found the term that produced Newtonian gravity in the limit. And so we're very interested in the idea that this might lead to new methods for symbolic regression. We're also very interested in the fact that when you greatly reduce the capacity of a model and reduce the number of free parameters, it really improves the possibility that you might be able to interpret your results. So for instance, in the case of our dimensionless scalars, so you have invariant dimensionless scalars, those are very interpretable objects. In fact, many of the dimensionless invariant scalars in physics have names like the Reynolds number and the Prandtl number and so on. There's various names for dimensionless scalars in physics, and they're very interpretable and very valuable. And a lot of insight has come from using those dimensionless numbers. We have various projects in progress, mainly in the cosmology domain. We're thinking of building some challenges for the machine learning world and so on. And there's my summary. Thanks very much.
Thank you, David. Appreciate it. That was really fascinating. So folks, you are welcome to ask questions. Some folks have put them in the chat, some in Q&A. So feel free to fire away. While you do, David, there's one other question that's been kind of lingering on any kind of suggestions or best practices for someone who's interested in contributing to open source software and open data sets.
Yeah, that's great.
Background in computer engineering or computer science.
Good. I have lots of feelings about that. And of course, one of the things I have to say, this is like slightly off topic, but one of the things that's great about being an astronomer is our data sets are really, many of them are completely public. For instance, all the data sets produced by NASA are put in the public domain with no licensing requirements of any kind. And many of the National Science Foundation supported and European missions have followed suit. And so a very large fraction of our data are pure open data with no licensing. And that's very exciting because it means that anyone can jump in and use it. So I think we're an incredible source. If you want to think about open science or try out data analysis methods or work in a real problem space, but you don't want to pay for data or sign non-disclosure agreements or whatever, we're a great place to work. So this is a good place to work. As to contributing to open source projects, that's another thing that's going on. Astronomy is super open source now. Almost all of the big codes and pipelines are completely open source and licensed under very open licenses like MIT. And so it's very easy to get involved. Our network is definitely GitHub, and we're very easy to find on GitHub, and you can find lots of projects in GitHub. And many of the big projects on GitHub in astronomy have very active projects pages and open issues pages. And so it's very easy to dive in and get involved. If you're interested at the intersection of machine learning or data science and kind of numerical things that are like scientific numerics or differential equations and things like that, there's lots of ways to get involved. You do not need to have either a computer science background or an astronomy background to be involved. Should I take them myself, Martha? Or are you going to choose?
Yeah, I mean, I'll let you pick and choose. I'd be happy for that. Would you like me to read them to you?
No, I'm reading right now.
Okay,
here's one. Transitioning from a space of latent variables to real observational models, can you identify bias in model building, possibly through incomplete understanding of all latent variables or through how the measurements are performed? Excellent question. My goodness. Yes, there's a lot of bias in the problems we work on because there's unidentified variables or variables we're not thinking about. And in fact, one of the things I've loved about this project is in these dynamics problems, when people were looking at how well they could predict the property of the springy dumbbell pendulum, which by the way is a toy, no one cares, it's just a toy. But when people build the toy model, they don't usually include the gravitational vector as an input to the problem, because why would you? It's the same in every instance. And we had to include the gravitational force vector into our problem, because otherwise we didn't have enough vectors to do our dot products with to make our complete set of scalars. And of course, so on the one hand, that's really bad because you have to think of all the things you have to include. But on the other hand, it's really good because once we included it, it gave us new generalization capabilities, because now we actually ended up getting a solution. Not only did our problem work better than other people's solutions, our problem is also equivariant to rotation. So you can now rotate the gravity vector into a different direction and we still make good predictions. So there's two sides of that. One side is, yes, you can easily miss important things that should be important parts of your problem. And if you do, you will bias your results and you will get wrong answers. On the other hand, when you do find them, you get new capabilities that other methods don't have. So I think that is hard. And one of the things I think that we're not making machine, I'm kind of like, oh, it's simple and it works, but we're not making machine learning easier, that's for sure, because we are requiring the user to think more about what are the physical inputs and require the user to think more about how to construct the invariants. And actually, one of the really interesting things is there are actually still open questions in permutation invariant features. So, we've been looking at whether permutation invariance, we've solved it for simple cases, but there's some complex permutation invariant cases where I'm not sure the answers are known, actually. So yes, that's a very, very good question. Another question, how would you envision symmetry laws being applied to machine learning for crystal structure? Oh yeah, good, crystal structure. Good. I only talked about physics. In fact, I only talked about astrophysics, but that's actually a mistake. Let me say a few things. One is a lot of the development in this area has come from chemistry, because the description of molecules, especially complex molecules, is a non-trivial problem. So chemistry, crystallography, biology, and lots of engineering things, computer vision, they're all places where these kinds of symmetry questions are important. That's one thing. Another thing is when you go into the units direction, we think about units and dimensions, there's a lot of applications outside of physics, including like we're working on an ecology problem right now with a sort of climate change direction, because, when you think of the inputs to climate change, those are things that have units. They're like tons of CO2 per person per year. And things about like the opacity of certain absorption lines in the CO2 spectrum. And you can put those things together and build a model for parts of climate change or the ecosystem that are units preserving or units invariant. So yeah, so we actually think, I've talked about astrophysics, but I think the applications are much broader, and I should have said that in my slides, and I apologize that I didn't. If real world data breaks symmetry because of the nature of the observations described, does that limit the upside to including symmetry considerations? Also, any room with combining with hidden Markov model style design that relates observer model to underlying model? Good, great questions. Oh my goodness. Yes, it's definitely the case that the fact that you have to put in an observation model that breaks symmetry hurts. That's a painful thing and definitely reduces the applicability and value of these approaches. However, in some cases, like in the cosmological case, we know the observation model really well. So we don't, in the case of cosmology, we don't have to learn the observation model. We know the observation model very accurately because we built the telescopes, we know how they work. There are other contexts in which there's uncertainties in the observation model, and then it's quite hard to see the symmetries in the latent physical model, because a lot of the data that are coming into your system are being used to really learn the observation model, and then they somehow don't flow information into the latent space where the symmetries exist. So I think there's going to be a big difference between problems where you understand the observation model and problems where you don't. And of course, most problems have a mixture. Like I say confidently, oh, we understand the observation model in astrophysics, but of course, there are foreground sources and noise sources that we're not accounting for correctly. And so we don't know it exactly. And so definitely that's a disadvantage. And you mentioned hidden Markov. Yes, I think hidden models where this hidden state is going to be a big part of what we're doing. And I think if you think about having to learn the observation model, which you have to in some cases, like you can think of neuroscience kinds of problems where, the brain itself is an object which obeys a bunch of symmetries, but your observation model is very, very related to that brain in a very complicated way. there, I think you might want to have a lot, you might want to be thinking of it in terms of hidden state and local information exchange between things in it with some hidden state. I don't know. I mean, we haven't figured that out at all, but that's exactly where we'd like to go next. Another question is thoughts on how much of this transfers to non-physical settings, social and economic. I said a little bit of that. I do think that it, as I kind of mentioned earlier, I think it applies to, you know, ecology and biology. Now, what about social science? So, you know, one thing that I'm interested in is macroeconomics. And macroeconomics, people don't tend to think with a units hat on, but physicists do. So, you know, you can think of like GDP per capita per year, you know, residents per country, the size of different industries. You could imagine building social science models that have dimensional properties. I mean, even like in most contexts, there's a way to see the things you're measuring as having units. Because some things you're measuring are per person, and some are per household, and some are per dollar, and some are per time. And because you have those different ways of splitting up the data, usually there are kind of dimensioned quantities, and they have to be combined in certain ways to produce a reasonable answer. So yeah, I'm hoping it could be applied in a wide range of settings. In fact, we're looking for example problems actually, because we would love, when we're writing this up, to give examples that go outside of physics, because as you can see from my presentation, we're very kind of physics oriented, but I don't think that's really a requirement.
Has any final questions before we close from the audience? So seeing none, thank you, David. Fascinating talk. I really appreciate your coming and giving us the time. And
it was my pleasure.
you again.
It was my pleasure. And if people want to get involved in astrophysics research, just drop me a line, because we are bristling with data. So, you know, if you need data, if you've got a hammer and you're looking for a nail, we have like rooms and rooms of nails.
Yeah, so thank you so much, David. And this is really a very enlightening talk. You know, it suits my own interest in particular. So hopefully we'll get another chance to talk to you more along those lines. This is very, very exciting. And
I'm
also
local. When we're open, we can all meet in person. We're only 100 blocks apart.
That's right. That's right. Yeah.
Excellent.
So
Thank you.
great. Thanks again.
Very much.
Thank you.
Thank you.